we will discuss about AVL tree. AVL tree is a special type of binary search tree. Before going into the concept of AVL tree, let's have a look on the basic features of the binary search tree. What is a binary search tree? The binary search tree is a tree where each parent node should have at most two children. At most two children. So we have like this, at most two children. Again, this parent node should have at most two children like this. Either 0 or 1 or 2, the number of children of each node should have. So this is not having a child, this is having only one child node, this is having only one child node, and this may have two children. So this is a binary search tree where each node, each parent node should have at most two children, either 0 or 1 or 2. So second property of binary search tree is, this is a basic property of binary search tree as well as a binary tree. Now the binary search tree, the second property is each node, the value stored is greater than the value stored in all the nodes of its left subtree and less than the value stored in all the nodes of its right subtree. For this particular node, let's have this node, the root node. Let's consider this root node where the value stored in all the nodes in the left subtree should be less than the value stored in this node, and the value stored in all the nodes of the right subtree should be greater than the value stored in this node. In other way, we can say for any given node, the value stored in that node should be greater than the value stored in its left child and should be less than the value stored in its right child. Right, this is the second property of binary search tree. So that the binary search can be applied in a smoother way, the binary search algorithm can be applied on this tree data structure. Now, what is AVL tree? AVL tree is nothing but a binary search tree, a special type, what is called the balanced binary search tree. AVL tree is a balanced binary search tree. Binary search tree. It's a balanced binary search tree. And what is balancing? And what is the difference between an unbalanced binary search tree and the balanced binary search tree? To understand this, let's study the concept of balance factor. Balance factor is equal to the height of the left subtree minus height of the right subtree. And the value should fall between -1 to +1. These three are the possible values. These are range of the values of the balance factor for which a particular tree we say as the balance tree. For a certain node, if the balance factor satisfies this range, falls within this range, we can say the subtree having that node as root is a balanced subtree. Otherwise not. For example, suppose in binary search tree, if we insert the elements like haphazardly without an order, so we can insert in this way. We can insert in this way in a haphazard manner, or we can see we can in this way. We can insert. We can insert in any pattern, any way, without any order. So the problem will happen in case of searching. When we want to search an element, when the searching is going to be performed, it will be very tough to search. There will be a difficulty in search. To make the searching process smoother and make that accessing a certain node will be tougher, and to resolve the problem, we have to balance the imbalance factor. So, how to judge whether it is a balanced or imbalanced tree? For a particular node, starting from the lowest node, starting from the node in the lowest level, we say that there is no subnode in the left, there is no subnode in the right. So the height of the left subtree is 0, the height of the right subtree is 0 for the last node. So the balance factor is 0 minus 0 equal to 0. That falls under -1, 0 plus 1. So this is balanced. And here for this node, particular node, the height of the left subtree is 1 because it passes through only one edge. It passes through only one edge to reach to the last level. So the height of the left subtree is only 1. The height of the right subtree is 0. So the balance factor is 1 minus 0 equal to 1. So these also falls under minus 1, 0, plus 1 range. Now for this particular node, the height of the left subtree is 1, 2 because it passes through two edges to reach to the last level. So the height of the left subtree is 2, the height of the right subtree is 0. So the balance factor is 2 minus 0, that is 2. So this is imbalanced, unbalanced. So this is, we can say this node is unbalanced. So the tree having this node as root node is unbalanced. And so we can say this node is also unbalanced, and so as this node is unbalanced. For this node, the left subtree, the height of the left subtree is 3, right subtree the height of the right subtree is 1, 2, 3. 3 edges it passes through to reach to the last level. So 3 is the height of the right subtree, and left subtree it is 0. So 0 minus 3 is minus 3, which doesn't fall under minus 1, 0, plus 1. So it is a unbalanced subtree. The subtree having this as the root node is the unbalanced subtree. For this node, we have the height of the left subtree 1, 2, 3, 4, and height of the right subtree is 2. So the balance factor is 4 minus 2 equal to 2. 4 minus 2 equal to 2. So it doesn't fall under minus 1, 0, and plus 1. So it is out of the range of this, out of this range. So we can say the tree having this root node, having this node as the root is a unbalanced tree. So this is unbalanced tree. And what is balanced? For example, what is balanced? The balanced tree is this. We can say a perfect binary tree, we can say as balanced tree, as well as this is also a balanced tree. Suppose this we have. Now see, for this particular node, we can say this is balanced because the height of the left subtree is 1, the height of the right subtree is 1. Okay. So we have this 1 minus 1 equal to 1 minus 1 equal to 0. So it falls under minus 1, 0, plus 1. For this particular node, we have the height of the left subtree is 2, the height of the right subtree is only 1. So the balance factor is 2 minus 1 equal to 1. 1 falls under this range. So this is also balanced. This is also balanced. And here we can say for this balance factor is the height of the left subtree is 1, 2, 3. 3. There are 3 minimum number of edges is 3 to reach to the highest level, or we can say this level. 3 is the height of the left subtree, and 1, 2, 3. 3 is the height of the right subtree. So the balance factor is 3 minus 3 equal to 0. So it falls under this range. So it is also balanced. For this, it is balanced or not balanced? This node is balanced, but this node is not balanced because left subtree, if I have a node here, so height of the left subtree is 1 and height of the right subtree is 2. 1 minus 2 is minus 1. This also satisfies this range, and this also satisfies this range. The balance factor is only 1. 1 minus 0 is 1. And so this is a balanced binary search tree. Now this we can say a AVL tree as well. So this is a balanced binary search tree where the height of the left subtree minus height of the right subtree equal to should fall under this range of the value should be within the range of minus 1, 0 and plus 1. From minus 1 to plus 1, this range. Now, how to make an unbalanced tree a balanced one? How to convert an unbalanced tree into a balanced tree? How to make the balancing? Now see, suppose we have this particular node under which we have this node, under which we have this node. Left, suppose this is A, this is B, this is C. B is less in value as compared to A, C is less in value as compared to B. So B is a left child of A because B is in value, B is less. As per the definition of binary search tree, the value of the left node or the nodes of the left subtree should be less in value as compared to the parent node. So B should be less than A and C should be less than B in value. So B is the left child of A and C is the left child of B. We have the balance factor of B. C is okay, 0 minus 0 is 0 because height of the left subtree is 0, height of the left subtree is right subtree is also 0. So balance factor is 0 minus 0 equal to 0. For B the balance factor is 1 is the height of the left subtree, 0 is the height of the right subtree, so 0 minus 1 equal to minus 1. So balance factor is minus 1, that is also okay because either minus 1 or 0 or plus 1 should be the balance factor. And for this A, this is not balanced because height of the left subtree is 2, height of the right subtree is 0 because no node in the right, there is no child node in the right of A. So we can say 2 minus 0 equal to 2. So 2 doesn't fall within this range. It doesn't satisfy the range, minus 1, 0, plus 1, 2. So this is unbalanced. A node, the tree having A as the root node is the unbalanced tree. How to balance it? The process, this is called left imbalance. Because why? Because we have left of it, two left childs are there, two left children are there, no right children, no right child we have. There is no child at the right either of A or of B. So we have left imbalance. How to remove this left imbalance? Only one rotation is required, that is called rotation. What is that rotation? We have to keep B as fixed and we have to rotate A clockwise. For left imbalance, we have to rotate A clockwise. Okay, one rotation is required, only one rotation. That is also clockwise. We will rotate A, keeping B as in the middle, keeping B as fixed in a compass. If you just rotate it clockwise, then A will come here. So it will just like this. It will just be like this. B, C. This is B the root node, C left and A right. So we can balance it. Now this has become the balanced one. Now, for example, these are the balancing. So there are 4 types of imbalances which we can balance and convert them into the AVL. How? Suppose we have left imbalance, we have the AVL. How it can be? 40, 30, 20. 3 elements we are going to insert in a binary search tree. 40, 30 and 20. Suppose 40 is the first node we insert as per the order. 30 is less than 40, so it will be the left child of 40. So that is 30, that is 40, that is 30. And 20 is less than 30, so it will be the left child of 20. But this is unbalanced. Why this is unbalanced? Because for 40, this particular node, the height of the left subtree is 2, the height of the left right subtree is 0. So the balance factor is equal to 2 minus 0 is 2. 2 doesn't fall under the range of minus 1 to plus 1. Now, so how to balance it? Just keeping 30 fixed, we have to rotate. So one rotation is required in that case. And by that rotation, clockwise rotation, that is also clockwise, we have to make 30 at the center, the root node 20. Keeping 30 at center, we have to rotate clockwise like this. Okay, and we can make 40 this way. So we can make it balanced. One rotation is required. One rotation right. That is a right side rotation is required. Okay, one rotation clockwise means right. Right side. That is AVL. What is RR? Means right imbalance. Suppose with the values just opposite 20, 30, 40. 20 first node, 30 is higher than 20, so it will be the right child of it, and 40 is the child of it, right child of it, because 40 is higher than 30. So we have this right imbalance. Right imbalance. So for which again one rotation is required. Only one rotation, and that is rotation is required, and that is anti-clockwise rotation. What is anti-clockwise rotation? Keeping 30th fixed in the compass, anti-clockwise rotation of the first node, like that. Okay, like that. So anti-clockwise rotation will make 30 is anti-clockwise. We can say at left is a left rotation. Left rotation towards left. So we have 30, 20, 40. That we must have. So this is right-right imbalance. Right-right unbalance. Now we have right-left. We have right-left. The third category, right-left. So when it is required, when it happens, when we have 50, 60 and 55. These three values, to insert these three values in a tree, but we have the right-left. First 50, the 60 will be the right child of 50 and 55 is less than 60, so it will be the left child of 60, 55. So what we have is a right-left. First right child, then left child. So RL imbalance. We can say RS imbalance, RL imbalance. So how to balance it? First we have to, for the left imbalance, what we have to do, the clockwise motion, clockwise rotation. Keeping this in the center, just to rotate it like this. Just to rotate it like this, 50 and 60 will change its location. We first convert it into the LL imbalance. First we convert it into the LL. For RR, I am sorry. First we have to convert it into the RL imbalance. First of all we have to convert it into the RR. So how to convert it in RR? Just this is the clockwise movement for left imbalance. The clockwise movement. 55 will come in place of 60 and 60 will come as a right of 55, like that. So 50, 60, 50, 55 and 60 in this way it comes, and 60. It comes like this, 50, 55 and 60. And after that it becomes the RR imbalance. Then we have to go for the anti-clockwise. Anti-clockwise means keeping 55 at constant, we rotate 50. Anti-clockwise direction. So finally it becomes 55, 50, 60, like this. So this becomes a AVL. This becomes a balanced VST. So when RL imbalance, we have two rotations. One rotation, this is a one rotation towards right, the right rotation, one right and one left. One rotation to the right and one rotation to the left we have. So one rotation towards right and one rotation towards left. We have two rotations. One to right, after right rotation we have these. We have 50, 55, 60. 55 will replace 60 and 60 will become the right child node of 55. So we have RR. We have the RR imbalance after this right rotation. Then the left rotation will make it an AVL. So for RL imbalance we have one right rotation followed by a left rotation. Now after that what we have? The LR imbalance. The LR imbalance. When it happens, if we have 60, 65, like that. Such type of entry. If such type of values are in this order, we have 70 is the first node, 60 will be the left of 70 because it is less than 70, and 65 is the right of 60, like this. So this is a left, right. So we can say LR. Because there is a left child, only no right child, so we can say left imbalance. Okay, there is a right child only, no left child, is a right imbalance. So it's a LR. total Euler imbalance is there. This is an unbalanced tree. So the Euler, this is a type Euler. What to do it? First of all, for right imbalance, to remove it, we have to go for the anti-clockwise rotation. What is the anti-clockwise rotation? Like this. Like this. This thing like this. 60 will come in place of, sorry, 65. 65 will, first we make it a LL. Likewise, in the RL imbalance, we first convert it into the RR imbalance. Then we convert it into the AVL, balanced AVL. Now here also, for LL imbalance, first of all we have to convert it into LL imbalance. Then we have to convert again the further LL imbalance to the AVL. So now, the clockwise motion, the clockwise rotation will give you 70, 65 and 60. This is the LL. Okay, this is LL. So we convert it into LL because the right side, the circular, the clockwise movement, the clockwise rotation, that will just replace 60 by 65 and 60 will come as a left child of 65. Just like this. Just you rotate like this and place here, we get the LL imbalance. Okay. Now what happens? After we have this, then we have to LL imbalanced, we just clockwise, we just rotate clockwise. So two rotations we have. First one is anti-clockwise, that is left, and next is clockwise, that is right. 70, giving 65 fixed, we just rotate 70 clockwise. One clockwise, that is right. So one left rotation followed by one right rotation. One left rotation followed by one right rotation. So that is will done. So 70 will come. So finally we have 65, 60 and 70. So these are all LL, RR, RL, LR. Such type of imbalances. How to balance them? How to just balance them? Now, before going into the example, let's discuss about the time complexity of binary search tree and the AVL tree as well. In binary search tree, what we have, the time complexity is log n. The time complexity is log n, where n is the total number of nodes. The time complexity is log n to find every node, where n is the number of nodes. Okay, n is the total number of nodes. Here the default base is considered to be 2. Here always the default base is considered to be 2. This means 2 to the power something equal to n. So for example, 1, 2, 3, 4, 5, 6, 7. 2 to the power something is equal to 7. 2 to the power less than 3. So actually the particular node, the height will be, the time complexity of such node will be 3, almost 3, because the highest level will be 3. First level, second level, third level. So the highest level is 3. So it is almost the height, the level is 3. So we can have. So if the n is 1, 2, 3, 4, 5, 6, 7, total 7 number of nodes, we have the 3 levels. Okay. 3 is almost equal to log 7 base 2. Almost, but not exactly. Because log 8 base 2 is 3. Because 2 to the power 3 is 8. So we have almost equal to. So what we say, the minimum depth or minimum time complexity what we have, that is log n base 2. That is a minimum time complexity. The minimum time complexity that we have at log n base 2. That is in case of best case or in case of the average case. In case of worst case, what will happen? The worst case, the time complexity is much more. The worst case, the time complexity will be in binary search tree. If there are n number of nodes, this is the worst case condition where the time complexity equal to n itself, equal to order of n. because it has to traverse all the n number of nodes to reach the last level's node. Okay, so the height of the particular tree and the time complexity to reach to the last level is order of n, what we can say. This is the worst case. But in this case, general case, we have log n base 2 is the time complexity to reach to the lowest level, or we can say reach to this particular level, the last level. Okay, the height of the tree is equal to log n base 2, where n is the total number of nodes, or height of the tree itself, the time complexity, to find a node at the last level. So, to search a node in the last level, that is log n base 2. And the worst case, the time complexity is n, because in worst case, it is either in ascending order or in descending order. Suppose this is in ascending order of values, like a linear data structure.